Hey guys, so today we'll go a little bit further into the Newton's third law of motion. Right, we'll try to understand what situations in real life we can see that adhere to this law. We already seen what happens when an object bounces, for example, right? That's about like when a ball hits a wall or something else hits a wall. These are all when a moving object collides with an object that is not moving. But what if I want to talk about when two objects are moving and they crash into each other? And does that law still apply? It will definitely apply. Okay, so to understand this, I will be talking about two objects. Okay, let's say that there are two balls. Okay, so these balls or spheres are moving in the same direction. Okay, they're both moving forward towards the right. Now generally what will happen for this object, I'll call this object as 1, this object is 2, right? Now if you see one object is bigger, it's a little different, so I'll just say okay, it has a mass of m1 and the other object has a mass of, let's say, m2, mass 1, mass 2. Okay, some difference in their mass. Now they are moving with some speed, right, some velocity, because I'm talking about the direction. What if this object is moving fast and this one is going slower? What happens is the distance between them will increase, right, because that will go ahead, this will stay back. But what if this object moves faster than this object? Okay, say that u1 is the velocity of this object that is moving and u2 is the velocity of that object. Okay, so m is nothing but mass, u is initial velocity. Okay, you'll see why I'm saying initial. So starting they are moving with that speed. Now if this object comes faster, at some point it's going to crash into this object, right? It's going to hit it. Now you'll see that, say if two objects are moving and one of them hits the other object, there's going to be some change in their speed, right? And once they crash, they will keep moving in the same direction but with different speeds. Their speeds are going to change. So I'll say that they take a velocity of v, final velocity. Okay, so I can put it like this, say that from here m1 and m2, okay, both these objects have crashed. If you see, they have hit each other. Now what happens, they again start moving but this time with a different speed. Okay, both of their speeds have changed. u1 changes to v1, u2 changes to v2. How much the change happens depends on the object, depends on the case. But for now we will say that two objects with this mass and this velocity crash, and after crashing they keep moving but with different velocities. The mass is the same but the velocity has changed. Okay. Now we know that third law says force by the first object on the second one is the same as force of the second object on the first one, right? But in the negative direction. So if I use this law and apply it to this, we know that force is nothing but change in momentum, right? So I can call this as delta P by delta T equals to minus delta P2 by delta T. Okay, if I see, I write P1 and P2 because each object has a different change in momentum. This is momentum for first object, momentum for second. And we know what is momentum. Mass into velocity. How much mass is that object multiplied by how fast it is going. If I want to see the change in this velocity, how do I see it? Okay, let's say that t is nothing but how much time they take when they crash, right? And that's a very small amount of time, so I just write it as t. So now I will say ki, what is the change in momentum for the first object? Okay, what is the change in momentum for the first object? So can I say that m1 v1 is its final momentum, right, minus m1 u1, which is the initial momentum, right? Momentum here is m1 into v1, here is m1 into u1, okay, divided by time. Same way for the second object, finally I have m2 and v2. Okay, remember there is this minus sign over here also, so minus of m2 v2 minus m2 u2 divided by t. Right, I am just replacing. Don't worry about all of these steps. Remember the case, remember the answer if you are finding everything confusing. Okay, but try to follow, it's best if you understand. Now if I simplify this minus, first thing I can do is I can cancel out the t, okay, because both are divided by the same time. So now m1 v1 minus m1 u1 equals to minus into plus, that is minus m2 v2 minus into minus plus m2 u2, right? Both of them have one negative, I will move them to the other side. Okay. This is V, not U, sorry. Okay, now I'll move the negative that side, m1 v1, and I'll bring this negative here, plus m2 v2 equals to, this goes there, m1 u1 plus m2 u2. Okay, this is the one that we are looking for. Try to remember this. What this tells me is m1 v1 plus m2 v2, that is the total momentum of both of these bodies, right? That is after colliding. So this is nothing but m1 v1 plus m2 v2. If I add their momentum over here, I'll get this one. For this case, it is nothing but m1 u1 plus m2 u2, correct? So if you notice, the sum of the momentums of both the systems is equal, is what this tells us. So this is called as law of conservation of momentum, or simply conservation of momentum. Okay, so the moment of these objects before crashing and the momentum after crashing, the sum, okay, that's why the plus, not individual momentum is not equal, right? So if I add their momentums before crashing and after crashing, the sum is definitely going to be the same. That is what law of conservation of momentum tells us. Okay, now we are going to be using this formula majorly if we have any sums going forward, which won't be today, in the next class.